Hello everyone! This is my last video in a series on exponential growth. This video will not be about a type of calculation or a type of formula, but instead about a special way to write down numbers, namely the scientific notation. In this video I will first explain what the scientific notation is. After that we will see how we can use this notation to write very large numbers and very small numbers. And for those small numbers, we will also have a look at negative powers of 10. And last but not least, I will explain why this notation is useful. And as always, I will end with a summary. So first of all, what is that scientific notation, also called standard notation? Well, a number written in scientific notation will always look a little something like this. It has two parts. One part that essentially tells us how big the number is, and then one part that specifically gives us the number. So to write it in this way, we will always have only one digit before the decimal point. So in this case, there's only the 2 before the decimal point, and everything else is after. The number may be rounded off. There may be more numbers after, in this case, the 4. But in this case, it was chosen to round off at 2 decimals. And as I said, it will always have a power of 10 that tells you how large, how big the number is. So let's have a look at an example for large numbers. So let's say I have this number and I want to write it in the scientific notation. And I've decided that I want to round off at 1 digit after the decimal point. That means that I'll have the 5 before the decimal point and the 2 after the decimal point. So the only numbers that I still need is this. Since the number after the 2 is a 4, it will round down, so it will be 5, 2, and then all the zeros. Now, as I said, we're going to have only one number before the decimal point, so that's 5. So it's going to be 5.2. But it's not just 5.2, it's 5.2 with a bunch of zeros. And that bunch of zeros we can say is, in this case, 1 billion times 5.2. This calculation, 1 billion times 5.2, is the same as my 5.2 billion that I had up there earlier. And then if I want to simplify this a bit, my billion has 9 zeros, so I can write that as 5.2 times 10 to the power of 9. 10 to the power of 9 being my 1 billion. So what I have is I have my 5.2 telling me the exact number, and my 10 to the power of 9 telling me that it has a total of 9 numbers before we actually get to the final digit. So that's the case for large numbers. Let's have a look at small numbers, and by small numbers I mean numbers like this. 0.0000 something. So numbers that are very close to 0 but are not quite 0. And as I said, before we can actually do this, we need to have a look at negative powers of 10. So let's put some powers of 10 in the table. The first couple we know, 10 to the power of 3 is 1,000, 10 to the power of 2 is 100, 10 to the power of 1 is 10. And in one of the previous videos we've seen that something to the power of 0 is 1. And you may notice a pattern here. Every step of the way, we divide by 10. So suppose we continue that pattern. If we divide 1 by 10, we're getting 0.1. If we divide 0.1 by 10, we get 0.01, etc. There's also another pattern here. 10 to the power of 3 has 3 zeros. 10 to the power of 2 has 2 zeros. Our negative powers do the same thing. 10 to the power of minus 2 also has 2 zeros, but in this case the zeros come before the 1. 10 to the power of minus 3 also has 3 zeros. So it's quite easy without making any calculations to write out powers of 10. Now let's use this knowledge with our small numbers. So let's say we're working with this one. 0.00000036. This one we won't have to round off, there's only 2 digits anyways. But we want 1 digit before the decimal point, so we want the decimal point to go here. So we want 3.6 times something. And that something is going to be lots of zeros, 0.00000001. We place the 1 where the 3 would have been. And as said, that has 7 zeros. So that's 3.6 times 10 to the power of minus 7. Another way you can think about it is how many steps do I need to move my decimal points to get to the point I need it to be. And if I count that, I get 1, 2, 3, 4, 5, 6, 7 steps. The decimal point must move 7 steps. So I get 3.6 times 10 to the power of minus 7. This way, we actually don't even need this step. We only need to count how many steps do I need to move my decimal point. Now, before I summarize this, let's have a look at why this notation is useful and why is this in a chapter about exponential growth. Well, first of all, one obvious reason why it's in this chapter, it uses 10 to the power of something, and this chapter is all about powers. But also, if I have exponential growth, then there's 2 ways that my graph can look. One we've already seen, it may look like this, where in this case the growth factor is a half. On the other hand, if my growth factor is, for instance, 2, so it increases all the time, it may look like this. It goes up very quickly. And if my growth factor is even larger, it's going to go up even faster. That means that with exponential growth, you easily get to numbers that are either way too small to work with, or that are way too large to work with nicely. If at some point you get to some number that's around 10 to the power of 21, it's 21 zeros, and a number that has 28 zeros, then they both look enormous, and you can't really compare anymore how large they are in the normal, regular notation. However, in this case, once you've written them in scientific notation, so with the 10 to the power of something, you know that they are about 10 to the power of 7 times larger than the other, because the power is 7 higher. So you know that they are, in this case, 10 million times larger. This takes some getting used to, and it doesn't immediately become obvious, but the more you work with this notation, the more useful it becomes, and the easier it is to see what is actually larger, what is actually smaller. So finally, let's summarize. So in all cases, we try to write the number with 1 digit before the decimal point. So that means that here the 5 is before the decimal point, and here the 3 will be before the decimal point. And also in both cases, we can just count how many steps the decimal point must move. In the right example for the small numbers, it's already obvious because we have a decimal point that we have to move between 3 and 6. For the large numbers, there is no decimal point yet, but it's technically here, we just don't write it. And it has to go between the 5 and the 2. So here the decimal point must move 9 steps, and in the example on the right with the small numbers, it moves 7 steps. Then if it's a large number, we just write the steps normally, and if it's a small number, we write it with a negative power to actually show that it becomes smaller, that the decimal point moves to the right instead of the left. And in this way, we can write any number in the scientific notation. So this was the last video on exponential growth. I hope you have found this series of videos educational and that you have learned something from them.